So here we have a simple circuit. A battery here, we'll just say 5 volts, doesn't matter at all. We have a resistor here, and we designate this thing down here as ground. Um, that's kind of what we would say normally for a circuit, but we don't necessarily have to do it. Ground could be relative to another voltage. So I'll talk about that in a sec, but before we get too far in depth, let's just think about this. So we have 5 volts here, and here we'll say literal 0 volts relative to Earth is that this is 0 volts relative to Earth, meaning Earth and this location on this wire are both 0 volts. So when you're talking about ground, Earth ground is probably the most true ground that you can get to, and that's kind of why you have the word ground in circuit terminology. But Earth ground is I think the thing that helps you understand ground the best. I would ask multiple people when I was studying electronics, like what does that mean, Earth ground? Because if you have some wire or something and you just shove it into the ground, it's just like an open circuit, right? And say you have like 5 volts here, and this right here, it wouldn't be different than like having a wire up here, is what I had originally thought about. And I was asking people and I couldn't get a straight answer, like, isn't this just an open circuit? So there's 5 volts right here. And kind of when you study Earth ground a little bit better, you realize that ideally, if you have Earth ground, and what really the best Earth ground is, true ideal Earth ground, when you talk about ideal components and whatnot, is a ground that sucks up all the current. So it is highly conductive. The ideal Earth ground is, you might be able to model it as just a huge sheet of metal, right? That might be a better, I don't know why we use this little triangle exactly. Maybe some of you might know. But I like to think of it as this huge sheet of metal, because that's what it is. The ideal ground is something that sucks up all of the voltage. So, I mean, when I say huge, I'm talking about like the size of the Earth or something. Just think about something that's really, really big. And allows you, or Earth itself, just the Earth is a giant ball of metal, right? Let's say. So there's very little resistance in that metal, and so you can say now that this is 0 volts, because this is no longer an open circuit. If it was an open circuit, you would have 5 volts here, but since it's not an open circuit, it is 0 volts. Meaning that obviously to go from 5 volts to 0 volts, you're going to need some resistance, right? In circuits, we know, like, you obviously need some resistance. So that's why, in circuits you do have some resistor there, because if this is truly, a superconductor or something, then there's going to be like no resistance at all, right? So it's basically saying, like, if you can kind of continue this idea that you have 5 volts here, and then here you have another circuit that's connected to the same ground, and here you have 10 volts, and this right here is connected to this ground right here. The idea of it being like very conductive is very important, because that means that if there was like theoretically some small voltage here, like 1 volt or something, 0.5 volts, and this was not 0 volts, that it would be it would basically suck all of the electrons, which is what we call voltage. It would suck all the electrons in itself. So I think like a giant ball of metal, the idea of the Earth being a giant ball of metal, but also something that it distributes the voltage all around, so that it's very, very close to 0 volts. And so for all practical purposes, you can call it 0 volts, because all of the electrons here are distributed everywhere. Even if there's a little bit of voltage right here, they'll all be distributed all across the Earth, and therefore it's 0 volts. And so that idea of true ground, ideal ground would be a soil that's very wet, so that the electrons are able to distribute, connect to each other over liquid a lot better. And so I hope that helps with the idea of ground, and what ground really means. So if you were to, in basic electronics, you kind of think of earth ground, but when you create an actual piece of electronics, most of those don't connect to earth ground. However, some do. I used to work on cellular boosters, and these giant pieces of cellular boosters did have a connection for earth ground in case there was lightning that hit near the antenna. Then it could go to the ground, and there wouldn't be any sort of the high voltage would go straight to ground instead of through the actual circuit. And you see that sometimes, like for example, you'll see that on like a power supply. You might connect to earth ground or something that's a larger ground, even though it might not be earth ground. For smaller circuits, like again going back to my cellular booster experience, when you have PCBs, your ground is not earth ground, but it is the same idea. When we think about like the soil, distributing these electrons all over, in a PCB you might have a bunch of traces everywhere and stuff. This is just a quick, here's a PCB with all these traces, and they connect in some way with resistors and all these components and stuff. But you want some way to dissipate those electrons so that they have somewhere to go in a PCB. So you have ground layers, or you might have traces, and then around these traces you would designate as ground, meaning this whole area is ground on the PCB. So that if you have some, and this kind of this is extending the idea again a little bit more to like RF stuff. But if you have really high frequency stuff, and you don't want it to be radiated out into the air, you want to kind of keep it inside. Radiated emissions is really important in RF. Then you ground it, meaning kind of it sucks any radiation that was there, or most of it that was there, to this ground. And in order to make it so that it's no longer radiated after it sucks to the ground, then it's distributed around a large area, and therefore this is now ground. So this part of the PCB that we designate as ground is not connected to earth ground, but it's the same exact idea of earth ground. It's some large area to suck all of the voltage so that there is around 0 volts left, because it's dissipated over a large area. And the only way that can happen is if ground itself is conductive, like what we talked about here with earth ground. Earth ground where there's dry ground, and if you put in like your earth ground for your house, not too far down the ground, and it's not moist enough, it's not a very effective ground. That's why you have to, for your house ground, have to go far enough so that there hopefully is some moisture there to be an effective ground. Otherwise, we go back to this idea of, if there's no resistance at all right here, then you just basically have an open circuit. So, instead of 5 volts, now you have a lightning bolt of, I don't know, some of you guys are probably a lot more accurate than me, but definitely a lot more accurate than me. We'll say 1,000 volts here. Well, now you touch the wire, you touch something in your house, and watch like Electroboom's video on if you can get electrocuted by being in your shower when a lightning bolt comes down into your through your electrical system, and then it can get, if it got to the water, could it kill you to death? He does fun experiences. His basic conclusion is that it's very unlikely, very very unlikely. But anyways, so you just touch this and you don't have a good ground. Now it's 1,000 volts. So obviously the concept of ground relies on some way to dissipate all of that energy through something like wet ground, So anyways, I hope that kind of clears up the idea of ground for some of you guys that are starting out, or maybe if you weren't super familiar with ground. Hope it helps a little bit. Let me know if I know that there's a lot of you that are a lot more knowledgeable than I have, but through experience, these are some of my concepts of ground that I've learned. And leave a comment below, and please subscribe if that helped you. Thanks, guys.